Hi everyone, and welcome to online lecture number 3 for our course. So, real quick before we get started, I hope everybody has seen that I have also begun uploading videos that cover example problems from the homework. I want to make sure to point this out because those videos are not only there to help you guys out on your homework problems, but also to illustrate the kind of work that I expect you guys to show when you complete the take-home exams that will be given to you guys later on in this course. Alright, with that announcement out of the way, let's jump right in. And we'll be picking up where we left off last time, with the fundamental theorem of calculus from section 5.5 in the textbook. I've already written out here what the fundamental theorem of calculus says. It tells you, in math speak if you would, that if f prime of x as a function is continuous for all values of x between a and b, then the definite integral from a to b of this derivative f prime of x dx is equal to f of b. Now that's the function itself, no longer the derivative, f of b minus f of a. Okay, in more plain English, what this is telling you, I've already written this out in red and in blue below, is that the definite integral of the derivative of a function is equal to the total change of the function. Okay, so this theorem, as it turns out, is well deserving of its name of fundamental theorem of calculus. And the reason for this is that it's going to make our life, ideally, quite a bit easier if we can get a certain thing done. And what I mean by this is that so far, in the last 2 lectures that we've done, the lectures from last week, we've been focusing quite a bit on this. This here, this definite integral, is our goal. We want to be able to evaluate these. But as we saw in the first online lecture that I posted, the only techniques that we really have for evaluating these definite integrals are techniques involving areas of rectangles, and we're basically trying to approximate area right now. And although that's doable, it is definitely possible to work through this, it's not particularly convenient. So this is generally pretty difficult, with what we have so far at least. This is not very straightforward. Meanwhile, this total change of the function, this is very easy. All we'd have to do is plug in and then subtract. So it seems like the much easier way of calculating these definite integrals is by just finding the total change of the function that they correspond to. And that's the catch, is that this requires that we know what that capital F of x is. And in many practical scenarios, you won't know right off the bat what this function is. Okay, and this leads us to the biggest question that we're going to be trying to answer today. And this question is the following. If you only know what f prime of x is, can you reconstruct f of x and then just use the fundamental theorem of calculus to compute any definite integrals. Okay, this is the big plan. The big idea here is, in many situations, you'll only know this left-hand side of this equation in this formula for the fundamental theorem of calculus. You won't actually know what's on the right-hand side, or at least you won't know what the function is that's over there. But that still doesn't mean that this isn't the proper way, or this isn't the best way to go about calculating this definite integral. So the goal now becomes to be able to reconstruct the function that you began with if you only know what its derivative is. And that's what we're going to be covering today. Alright, so that leads us now to get into the new chapter, and we're going to be talking now about antiderivatives. And I want to point out that this is from section 6.1 in the textbook. Okay, so antiderivatives are defined exactly the way you'd expect them to be. So we say that f of x is an antiderivative note just a quick notation thing. We do like to use this capital F when we're working with antiderivatives. Anyways, we say that capital F of x is an antiderivative of the function lowercase f of x if the derivative of capital F of x is equal to our lowercase f of x. Okay, so in other words, if I were to try to present this information perhaps more visually, we have learned so far in this course how to, if you're given a function f of x, we have learned how to find its derivative. And now the focus is on learning to do the opposite process, which is called finding the antiderivative. Now, before I get into this, and before I get into all the different rules, there is a note that's worth making. And this is really an aside, but it is important to mention this. So if you're given a function, then this actually has many different antiderivatives. And the reason for this is that when you take the derivative of something, any constant disappears to zero. So, for example, if I take the function x squared, this is an antiderivative of the function 2x. But so are the functions x squared plus 3, or x squared minus 2. And you can check this by seeing that if I take the derivative of any of these three functions, if I take the derivative of x squared, if I take the derivative of x squared plus 3, or if you take the derivative of x squared minus 2, they're all going to give you 2x. All right, so let's make a long story short and just say that just in general, if capital F of x is an antiderivative of lowercase f of x, then capital F of x plus c is also, or is too. And that's true for any constant c. So as long as c is just a number, you can add any just number to a function, and you won't change what it's an antiderivative of. Okay. And the last thing I sort of want to focus on today, which is going to be a good amount to take in, but nevertheless, this is very analogous. So just like we have rules for finding derivatives, we're going to have rules for finding antiderivatives. All right, and what I'm going to do for the rest of this lecture is just to go through all of these different rules, and you'll find that they're all pretty similar to the rules that we had for derivatives, and in fact, they're basically just going to be reverse engineering those. All right, so let's get to it. Okay, so first things first, the process of finding the antiderivatives of a function is called taking an indefinite integral. So real quick, we denote these with the same symbol we used for definite integrals. As this integral symbol of f of x dx. And note there are no a's or b's here. So in other words, there's none of what we call limits of integration. And we use this to indicate the indefinite integrals, or integral, of the function f of x, which represents all possible antiderivatives. All right, this may seem complicated, but basically what I'm trying to say is the process of doing the opposite thing of taking the derivative, so in other words, the process of finding the antiderivatives, the notation we're going to use for this is this. We're going to use this integration symbol, an f of x, and don't forget your dx. This dx just indicates that x is our variable. That's it. It doesn't do anything special. It's just telling us that the variable we're using is going to be the variable x, and that's what we're talking about here. If you ever were to go on and take a multivariable calculus course or anything like that, then that would matter more. But this is obviously a calculus course for non-majors. So basically what I'm going to say is don't forget to write the dx, but in most cases for you guys, it's not going to be very important. All right. And now with this said, with this written out, now that we've established this notation, I'm going to jump right into the rules. And these rules are going to basically be reverse engineered from the derivative rules. And what I mean by that is that if we're trying to do the opposite process from taking the derivatives, then all of our rules are going to do the opposite thing from what the derivative rules were doing. And the very first one in which you can see this is the power rule. And the power rule for antiderivatives, or for indefinite integrals, is as follows. This is the rule. You guys should remember this. If I'm taking the integral of x to some power n, remember x to the power n is just some power function, then this is going to be equal to 1 over n plus 1 times x to the power n plus 1. And don't forget the plus c. All of our rules are going to have these. I'm going to put this out in red. I'm going to mention that this plus c is going to show up at the end of every indefinite integral. It's going to be there every single time because remember we're trying to capture all the possible antiderivatives, and antiderivatives, as we mentioned earlier, are only defined out to a constant. So basically what I'm trying to say is don't forget your plus c, but otherwise don't worry about it too much. The important part about this rule is this part in blue over here. All right, I think it's really helpful to go over some examples. And give me just a second here. Let's make this a little bit smaller. And let's jump into some examples so you guys can see what happens. So first example would be the integral of x squared dx. And this is going to be x to the new power, which is x cubed. Remember, 2 plus 1 is going to be 3. And then in front, we divide by the new power, plus c. So my suggestion is first, find the new power. And then divide by the new power. In front. All right, so here we were integrating x to the power 2, And so we got x to the power 3 and then dividing by 3 in front. And again, don't forget your plus c. That's going to show up in every single indefinite integral problem that we do. Regardless of the rule, that's always going to be there. Okay. Let's move on to another example. So let's do another example, maybe a bit more funky. Let's do this time the integral of x to the power 11 dx. And you'll see that this is going to give us x to the new power, which will be 12. And we divide by 12 in front and add c. We can take the integral of x to the power negative 3. And this is going to be x to the new power. Negative 3 plus 1 is negative 2. And we divide by negative 2 in front. We can do integral of x to the power 1/2. That's square root of x, remember? This is going to be equal to x to the new power. 1/2 plus 1 is 3/2. And in front we divide by 3/2 plus c. Okay, so that's what I've got basically for the power rule. But at this point is a good time to mention that there is one exception to this power rule. And this is going to look familiar to you guys, because this is going to bring us to our second rule. So this is one exception to the power rule. And this is the following. It's a very specific rule, but it's very important. This rule tells us that the integral of 1 over x dx, and keep in mind that 1 over x is equal to x to the power negative 1, and that's what I mean by an exception here. You're not allowed to use the power rule on this one. Instead, it turns out that this is the log rule. Okay, there's really no examples for me to give here. This is the only function that's an exception to the power rule is in the case of 1 over x, and this rule only applies to that function. So there's no other example for me to cover here. This is the only function that this is relevant to. All right, so we've got our power rule. We've got our logarithm rule. What's left is our exponential rule. And you guys will like this one, because just like exponentials are really easy and nice for derivatives, they're also very, very nice in integrals. And the reason for this is that the integral of e to the x is just e to the x. There's nothing to undo here, since derivatives don't change e to the x, neither do integrals. And once again, there's no examples for me to give here. There's no additional comments to make, really. All I can really tell you guys is that when you're taking the integral of the function e to the x, integration doesn't change it any more than taking the derivatives do. Okay. So now that I've given all these rules, I'm going to list them out again. So first we had the power rule. And the power rule told us that the integral of x to the power n is equal to x to the power n plus 1. And then up front, we divide by that new power n plus 1 plus c. We had the log rule, which told us that the integral of 1 over x dx is equal to the natural log of x plus c. And we had the exponential rule. And the exponential rule told us that the integral of e to the x dx is equal to e to the x plus c. Okay, these rules are super helpful. They're very similar to the power, log, and exponential rules that we had for derivatives. But on their own, they're not quite enough to allow us to attack a lot of different problems. So if you guys remembered, when we covered rules for derivatives, I mentioned that we have rules for all the basic or elementary functions, like we call them. And that was the power rule, that was the log rule, that was the exponential rule. And then I mentioned to you guys that also important were rules that allow us to combine different functions together and to figure out what their derivatives were. And so I'm going to call these combination rules. Combination rules tell us what to do when you're taking the integral of two different functions combined together in some way. And the first is the addition rule. And the addition rule tells us that the integral of, let's say, f of x plus g of x dx, that's equal to the integral of f of x plus the integral of g of x. So if you're integrating an addition, you can split up into the addition of the integrals. And then we have the constant multiple rules, which tells us that if you're taking the integral of a times f of x dx, this is equal to a times the integral of f of x dx. And this, of course, holds if a is just a constant number. All right, I want to emphasize something real quick here, which is to say that the combination rules what I'm calling the combination rules for integrals are the same as for derivatives. Right? So for derivatives, we are told that if you're taking the derivative of a sum, that's just the sum of the derivatives. And if you have a constant multiple inside a derivative, you can just pull it out in front. The exact same thing is true for integrals. The integral of the sum is a sum of the integrals, and if you have a constant multiple inside an integral, you can just pull it out in front. So those two things are going to be exactly the same for integrals as they were for derivatives. All right. Now this does lead to the question of why did we need to have these combination rules? What do these allow us to do? And to show this, I'm going to do a bunch of examples here, and then I think we're going to call it a day. So let's leave these rules up here. give us some more space to do some examples. So the first off is, what if I take the integral of 3x squared dx? This is going to be equal to 3 times the integral of x squared dx. And how do I know this? This is by the constant multiple rule. So this 3 is going to stay in front, and now this is going to be equal to 3 times our new power of x is going to be 3, dividing in front by 1/3, plus c, and this is by the power rule. So this is how you'd find the integral of 3x squared. You'd first use the constant multiple rule to pull the 3 out, and then you're just left with the power rule, which is pretty straightforward. Okay, another example. Let's do the integral of x to the 7th plus e to the x dx. Now this is going to be equal to the integral of x to the 7th dx plus the integral of e to the x dx. And we know this by the addition rule. Now we can do each of these integrals separately. X to the 7th, our power rule tells us that we increase this power by 1 to get 8. And in front we divide by the new power, which is 8. Plus e to the x we know does not change. And then plus c. So this here was power. And this here was exponential. Okay, let's do some more examples. Get maybe a little bit more intricate. Let's do a polynomial, right? Remember, polynomials are just sums of power functions with numbers in front of each power of x. So let's say we're going to do 3x to the 5th plus, I don't know, 7x to the 4th plus 9x minus 1. All right. So this is just an addition of a lot of different functions, so we can just do each of these one at a time. So for the first one, we have a 3 up in front that's going to stay there. Now, the integral of x to the 5th is going to be x to the 6th and divide by the new power in front. Next, we're adding, and we have the 7, which is going to stay there as a constant multiple, times the integral of x to the 4th, increase the power by 1 to get x to the 5th, and divide by this new power in front. Next, we have 9. It's going to stay in front, times the integral of x. So the new power of x is going to be x to the power 2. And now we're going to divide in front by the power, which is 2. And last but not least, what do we do with this 1 over here? Well, this 1, I want to note that 1 is equal to x to the power 0. And so as a result, this is actually also going to be a power rule. We have x to the power 1, and then we're dividing in front by the new power. So the integral of 1 is x. And don't forget your plus c. So the integral of a polynomial is just done by using the addition rule, the constant multiple rule, and the power rule a bunch of times. This shouldn't be all that difficult once you get a good handle or a good hang of the power rule for integrals. These are not significantly harder than finding the derivatives of polynomials, and they're still pretty straightforward. Okay. Let's do just a couple more examples. Let's do the integral of 7e to the x minus 2 over x dx. Okay, so this isn't going to be much more complicated than any other problem. First, we're going to split this up using our addition and constant multiple rules to see that this is going to be equal to 7 times the integral of e to the x dx minus 2 times the integral of 1 over x dx. And to see this, I've used the addition rule and the constant multiple rule. Now all that's left is to use the exponential rule, which tells us that the integral of e to the x is e to the x, and the log rule, which tells us that the integral of 1 over x is natural log of x, and we get our final answer. Okay, so these are just the most straightforward, the simplest rules for finding indefinite integrals. There's not going to be very many rules beyond this. We're only going to cover one more complicated rule, which is basically going to be the integral equivalent of the chain rule. But don't worry, we're not going to do that until a little bit later, and there's not going to be any equivalent of the power rule of the product rule, nor is there going to be any equivalent of the quotient rule. So you don't have to worry about that. We're not going to cover quite as many rules for how to do these integrals. So mostly we're just going to stick to the pretty basic elementary function rules, and this should feel pretty similar to doing derivatives. The only thing I'll say about this is try to not get too mixed up between the power, log, and exponential rules for integrals and the ones for derivatives. It's pretty easy to forget which one is which, so try to keep them nice and separate in your head. And what we're going to do here, at least for now, shouldn't be all that much more difficult than what we've done for derivatives so far. All right, that's about it for what I have today. I just want to mention that I'm going to have a lot more practice problem videos coming up. I know that there's a lot of problems on the homework set that I assigned that I haven't yet done videos on. I'm going to try to keep those coming so that everybody can see these. And worst case scenario, do not worry if you have to turn in the assignments late. At this point in the course, I honestly don't really care about whether you submit all of the homework sets by the due date or not. As long as you get all of those done by the end of the semester, I will consider them done for you guys. So if you feel like you need to wait for me to put out the videos on the problems that you're worried about, go ahead and do so. I'll try to put those out as quickly as possible. And as always, if you have any questions about any of the materials in this lecture or any of the material that shows up on any of the homework sets, just shoot me an email, just let me know, and I'll do my best to help you guys out. All right. Hope you guys are all staying safe and healthy at home, and that'll be it for today. Bye-bye.